General Physics 1. And now, here's your professor, Viranga Pereira.
Hello everyone, welcome back. We have started talking about two-dimensional motion last time, so we'll continue doing that. And towards the second half of the class, we'll talk about Newton's laws. Going to our computer here, I'm showing this video of someone playing ping pong. And I talked about different kind of objects that are likely to follow projectile motion before, right? So a golf ball, for instance, if you're playing basketball, right here, tennis, ping pong, that sort of thing. So if you're kind of seeing this in everyday life, right, pay attention to that. Where is an object that you see kind of following this projectile motion path, right? So going to our learning outcomes now, for today, we're going to talk about projectile motion, work out some math and do some problems associated with projectile motion. And like I said, we'll get into Newton's laws today. There's a reason why we'll start with the second one first, and you'll see. So we'll get into all of that in a second. But first, let's look at this demo video. It gets us thinking about projectile motion, and particularly the idea that the two motions in x and y are independent of each other, right? So I mentioned that last time. It's a really critical idea. So let's take a look at this, and we'll come back after. In this demo, we're going to look at two-dimensional motion. We have this device, this cart here, that is going to have a ball inside, and the ball is going to get kicked up because there's a spring that's going to kick the ball up vertically as it passes this point. So there's a point here, and at this point, it's going to get triggered. The ball's going to go straight up. So the cart's going to go through this tunnel, and what I want you to do is think about what happens to the ball as this cart goes through the tunnel. Like I said, the ball is going to have this vertical velocity, the cart has a horizontal velocity, and what happens on the other side. So take a second to think about that. Okay, so what we're going to do now is to put the ball in. Now it's in there, it's going to get triggered at this point, it's going to get kicked up, and let's see what happens. Okay, so the ball comes back and falls into the cart, this container. It's able to go above the tunnel and fall back in its place where it started, and that's because it also has a horizontal velocity, not only the cart. So the cart has some horizontal velocity. The ball, in addition to the vertical velocity it gets by this kicking it up, it also has a horizontal velocity. So that's why it's able to go in a parabolic path and end up back where it was at the beginning, which is inside this container. So the container moves at a certain rate, right? So it has a certain horizontal velocity. So that's why the ball is able to basically track that cart and fall back to where it was. And this is illustrating how motion in two dimensions is independent. So the horizontal component of velocity is independent from the vertical component of velocity. So the vertical component is governed by gravity, which is pulling it down, but in this case we're trying to minimize friction, so the horizontal component should be fairly constant. So this is, again, a demo illustrating two-dimensional motion. Okay, so last time we looked at this, right, so projectile motion, and I drew this picture of how an object might follow this sort of path, right? So in the demo, when you're seeing that ball get kicked up, it kind of follows this path. And at any point along the way, you can draw a velocity vector, right? Showing you what the velocity is at any single point. And we talked about how that velocity vector changes over time, right? So you can show that it's horizontal here, it's kind of at this angle here, and so on, pointing kind of downward here. So we have talked about vectors, right? So you can take that velocity vector and write it in component form in the x component and the y component. And using this idea that these two components, x and y, are independent of each other, we came up with a set of equations right? Assuming that there's a constant acceleration in both directions. In one direction is 0, the other direction is negative 9.8 meters per second squared. And based on that, we came up with some equations, right? These are still the kinematic equations, right? So there's still the 4 we talked about at the very beginning for one-dimensional motion, but now we're just applying those 4 as needed for x and then y, right? So just come up with some equations that models how this object moves through space. Okay, so let's try to practice this. Okay, so talked about playing golf on the moon, so let's talk about being back on Earth. There's a stone that is thrown from the top of a building. So take a look at this problem. Don't forget, draw a picture first, right? Identify what you already know. Make a plan that how you're going to approach to solve this problem. Take that time, right? Don't rush into trying to solve, quote unquote, the problem directly. Take your time, think about what's going on, draw a picture, try to identify what's happening, and we'll go from there. So let's pause for a minute and a half, have you work on it, and we'll come back. Okay, quickly checking the questions. Okay, so keep working on it. Looks like you're still working on it, so that's okay. If you have questions, don't forget, throw it on Ed Discussion, and we'll take a look at that. And let's take a peek at my notes here. And you can see this is what I start to do right from the beginning. It's just while you're doing it, I'm also sketching on the side, right? So I'm trying to put a person on top of a building. Here's the ground. Right? It doesn't have to be too fancy. Like I said, if you're artistic, make it artistic. If you're not, just this is sufficient, right? All you need to do is to capture just the essentials of the problem, right? So keep working on it. We'll switch back to the computer and take another minute and keep working on it. We'll keep checking on you. Okay, is there a question? Yeah, we can use 9.8 meters per second squared.
If you use 10, that's okay. It'll give you a slightly different answer. But whenever possible, use 9.8 meters per second squared. Okay, so keep working on it. Some of you have answers in. If you don't, maybe you're still working on it. That's okay. So let's switch to the DocCam here and see what I have so far. All right, just compare with what you have in your notes as well. Here's my building. Here's a person on top of the building. Here's my stone. I've drawn the stone bigger, of course, just to see it. And then I put the vector for the 20 meters per second, right? And then there's a certain angle to that speed that makes it a velocity, right? So 30 degrees. Let's see, we capture everything 45 meters up in the air, right, off the ground. And so that's what the problem gives, right? So that's, everybody can agree that's what the problem states. Here's where you and I and maybe your friend, right, you all can disagree on where you put the coordinate system, right? What does it mean to be 0, 0 in x and y? Now, I could pick this point, right, where the stone starts. I can say is the 0, 0 point. You can alternatively put the coordinate system at the bottom, right, so that y and x shows up here, or you can put the coordinate system here or here, right? So you can put the coordinate system wherever you like, and you might say, well, I don't know where I should put it. There's so many options. You just put it wherever is most convenient for you, and so when you're first starting off, it might not be obvious that is this more convenient or is this more convenient. You can probably agree that putting the coordinate system somewhere here is not very convenient, right? Because there's no reference here there's no building that we know of, right? So it's just somewhere in the open space. You're just randomly assigning the coordinate system there. Not a great choice, right? So could you put it at the bottom of the building? Sure, no problem. Could you put it at the top of the building? Sure, no problem, right? So you just kind of pick a convenient point. It doesn't change the result of what happens to the stone, right? Because you use a different coordinate system. It's mostly to make your life as easy as possible, right? So I'm going to choose the coordinate system up here. And that does mean my y values are dictated by my coordinate system, right? So when I say my initial y value of the stone, because of my choice of my coordinate system, it's 0 meters. Right? It starts off at 0 meters from the y-axis, right? It's at 0, 0 point. And when it falls to the ground, so we might draw the trajectory of the stone, maybe it kind of does something like that, right? And when it gets over here, we have to figure out what is the y value final, right? Is negative 45 meters, right? That's consistent with our coordinate system. Now, if you put the coordinate system down here, these numbers would be different, right? Your initial would be positive 45 meters. Your final would be 0 meters, right? And again, doesn't change the physics, right? The numbers themselves are different, but then at the end result will be the same, right? So how long it takes for the stone to reach the ground is the same number regardless of where you decide to put your coordinate system. And as an exercise, you might want to try it out with 2 different coordinate systems, right? So I made a video posted on a discussion, the link, where I do this intentionally, where I use different coordinate systems just to show you how you should be getting comfortable with using different coordinate systems, right? Okay, so this is, see how much time I'm taking at the beginning to set this problem up. I haven't used a single equation, I haven't plugged in a single number to my calculator, and especially when you're starting off, spend a lot of time on these steps, right? Drawing pictures and identifying what is given, what's going on, right? Try to imagine the movie of the stone, right? Or actually go out, pick out a stone and throw it, right? So it's always better to actually do this in real life. Okay, so then what you want to do is to think about, okay, what's the physics? What is the equation, right? What's the concept that we want to try to apply? We're still talking about kinematics, describing motion. It's 2-dimensional now, right? And we need a kinematic equation, or maybe more, that gets us time, right? That's what we're asked to find. How long does it take to fall to the ground, right? So looking at your notes, right, looking at the 4 kinematic equations, you have a couple options, right? And I'm going to propose this one. Okay, as we talked about, just pick one of the equations, try to work with it. If you get stuck, no problem, use a different equation, right? So just kind of reason your way through the equation. Let's pick this one. Let's see why is this a good choice, right? It has time, that's good. We're solving for time. We have the acceleration due to gravity, right? We know that on Earth, the acceleration in the y direction here is negative 9.8 meters per second squared, right? So we have that number for A. Velocity initial, we sort of have some information about that, right? So we kind of have this 20 meters per second. And then we have the y values before and after, right? Okay, so let's kind of check off what we know. So the final y is minus 45 meters. The initial y, 0. This initial velocity is not 20 meters per second, right? Because we're talking about the initial velocity just in the y direction. This is a vector, we're going to have to break it up. But we'll put a question mark there. We know something about it, we'll come back to it. And certainly this is known, right? So it's not negative 9.8 meters per second squared, right? So we have a lot of what we need, and then we can solve for t, right? Let's think about this initial velocity in the y. What I'm going to do is draw that vector, 20 meters per second, right? Our velocity vector, and break it up into its component parts, right? So when I'm doing this, I'm trying to make a right triangle, and the 2 sides of the right triangle are not random. They're following the y-axis and the x-axis, right? They're following my coordinate system. See, the x-axis goes like this. So when I draw a line to break up my vector, one of them goes like this, right? One of them is horizontal, my y is vertical, therefore one of the lines of the right triangle is vertical, right? So when I look at the vector itself is always the hypotenuse of a right triangle, but the 2 other sides of the right triangle just follow the x and y, and you'll always form a right triangle, right? And we know this is 30 degrees. This side is the y component of velocity. This side is the x component velocity, right? And we need this for our equation. We need it for this, right? So how do we solve this? We use our mnemonic, SOHCAHTOA, for our trig, right? We have this angle 30 degrees. Which one do we use here? We're trying to find 30 degrees, this is opposite side. 30 degrees opposite is this, right? So we need either these two. We have the hypotenuse, and that's why we want to use sine, right? Because sine is the opposite of the hypotenuse. We're trying to solve for the opposite. We have the hypotenuse, right? So what that means is you can say, well, sine of 30 degrees is equal to its opposite, v naught y, divided by the hypotenuse. I'll just call it v, right? The 20 meters per second, I'll just call it v. And then when I solve for it, v naught y is equal to 20 meters per second sine of 30 degrees, which is going to be 10 meters per second. Okay, so again, watch out for your calculator. Make sure when you're putting 30 degrees into your calculator is in the degrees mode, right? It can be either in degrees or radians. If it's in radians, it's not going to give you the correct answer, right? So we will use radians sometimes. So we will put in a 2 pi into sine sometimes, right? So in that case, you do want to flip to radians. Okay, so we have everything we need up here to solve this. Right? So what we're going to do is put everything in, pieces of the puzzle together, so we see that, right? So notice I'm figuring everything out before I throw numbers into this equation, but now I have enough to go ahead and do that. negative 45 meters is equal to 0 plus 10 meters per second times time minus 1/2, 9.8 meters per second squared times squared. Oops. Right? So I'm just taking this equation and plugging in everything we know we've sorted out. And what I'll do is rewrite it slightly, right? So I'll say 0 is equal to minus 1/2 times 9.8 meters per second squared times squared plus 10 meters per second times time plus 45 meters. Okay, and this should take on a form, hopefully, that is a little familiar to you, right? And from your math class, you probably remember the quadratic formula, right? Which goes as ax squared plus bx plus c is equal to 0, right? So if an equation takes this form, there's some constant to some variable squared plus another constant times that variable plus a constant is equal to 0. If there's an equation that takes this form, you know there's the solution, which is that x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a, right? Now, you don't have to memorize the quadratic formula. This will be in your equation sheet, right, if you need to use it. So either you use the quadratic formula or your calculators often have this built into it. So you can Google and search how your particular calculator can solve a quadratic formula. So you should be able to enter just this and have it tell you what t is equal to, right? So that's a lot faster if you kind of spend some time figuring out how you solve quadratic formulas in your own calculator. It will speed up this calculation process. But alternatively, you can just use this, right? You can actually plug in the constants into this formula and it'll tell you what that is, right? So x here is x is some variable. So in this particular case, what we're talking about is t, right? That's our variable. So if you use the quadratic equation or you use your calculator, either way, doesn't matter to me, you're going to get time is equal to 4.2 seconds. Okay, so try that out yourself. Don't just take my word for it, right? Make sure you're trying this out. There's a lot we covered in this problem, right? It's a nice problem because it goes over a lot of different things, but we'll pause, make sure all your questions are answered here, right? And before we proceed, so let's pause to check. How are you doing in terms of questions?
We have questions about solving using the max height. Some people are solving for the time it takes to reach the max height first, and then solving for a free fall equation. Yeah.
So that's good. So there are different ways to solve these sorts of problems, right? So if you are, some people are talking about, well, can I calculate the maximum height? So if you use what we did last time in class and figure out the maximum height, and kind of work time that way, you're going to get a time that takes the stone to get to this point, right? And then after that, you'd have to still carry on another calculation to get the other time, and then you can add those two times together, and you should still get this number, right? So with kinematic problems, there are different ways to solve it, and it's highly encouraged for you to figure out different ways to solve it. Some are faster, right? I'm not saying this is the best, right? This is kind of a way of doing it, but if you have different ways to solve the problem, as long as you're consistent, right? So that means that when this stone leaves, it follows this path because we know in reality that's what it does, and it's not going to take off and go to the moon or whatever, right? So like, as long as the physical reality is consistent, then you can do different approaches in terms of your mathematical solution, right? Other questions about this, particularly how are we on vectors, right? So we do want to make sure we're strong, right, in this component, because when we talk about forces later today and then going to future classes, we are going to have to deal with this, right? We want to break up vectors into component parts. So make sure you're okay with this. Ask me questions of this part of it, right? So there's some kinematics going on, there's some trig going on, right? And some algebra at the end, right? So there's different components to solving this problem, right? So make sure that every part is okay. Any questions other than that? What are some of the common things that are coming up, kind of generally? The trig, SOHCAHTOA stuff, or?
Yeah, just like the usage of sun.
Yeah, so kind of do some practice on your right triangles, right? On Ed Discussion, I started a category called resources, right? So you're welcome to share resources about right triangles, trigonometry, that sort of thing. If you want specific help in certain areas, just kind of post that, right? So let us know what's confusing, and we can happily help with that. So make sure that this is critical, right? So if you're looking at SOHCAHTOA, for instance, right, knowing that the sine of any angle is the opposite over the hypotenuse of this triangle, that you should kind of be familiar with. If you're not sure about that, right, let us know. Don't forget, on Quest, there are physics readiness modules, right, one specifically on trigonometry. So make sure you're jumping into that just to brush up on your trig. Okay. We're good to go to the next one? Good? All right. So let's continue with this problem, but let's ask a different question, right? So go into our computer here, right? So same stone being thrown from the same building, right? Same angle, same speed, right? Height of the building is the same. Now it's asking, what is the speed of the stone just before it strikes the ground, right? So after it strikes the ground, right, that's pretty clear, it comes to rest. But just before, right, say 0.1 seconds before it strikes the ground, very small time period before it strikes the ground, how fast, right, speed-wise, we want the magnitude of velocity, speed, how fast is it moving, right? So I'm going to pause here for a minute, have you think about this, and then we'll come chat about it. Make sure you're asking questions on Ed Discussion in the meantime, and be back in a minute. Okay, so keep working on it. No rush here. Just trying to have you work on. Are there questions about this particular one yet, or
Not this
not
one.
yet? Okay. Anything from the previous one?
Nothing we haven't
Okay,
answered.
cool. All right, so keep working on this, right? So make sure you're drawing a diagram, right? So your diagrams can be different. Maybe for this one you want to use a slightly different diagram. It's up to you, but don't skip that step, right? So let's switch to the DocCam to see, how would I draw this, right? Okay, so I'm going to draw that initial velocity, 20 meters per second, and put in the angle was 30 degrees, right? And notice I'm thinking about already, this is a vector, I'm breaking up into component parts, right? So I have the x part and the y part, and keep breaking them up into x and y because x and y are independent, right? So they function independently. So we want to always be thinking about x being separate from y, right? So in the previous step, we already did one of them, right? We said that this part, right? So the velocity is made out of two components, the x part and the y part. The y part, v naught y, we said was equal to 20 meters per second sine of 30 degrees, which is equal to 10 meters per second, right? We did that in the previous step, but we can also do that for the x, right? So y naught x will be equal to 20 meters per second cosine of 30 degrees, which will be 17.3 meters per second, right? So again, doing a little SOHCAHTOA, right? For 30 degrees, it's adjacent over its hypotenuse, right, is cosine 30, right? Cosine 30 is adjacent over the hypotenuse, this side, the adjacent side, over the hypotenuse, right? So that's why we use cosine. Don't get in the habit of associating y with sine and x with cosine, right? That's not a good idea. Oftentimes that's the case, but it doesn't have to always be that way, right? So imagine if this is the angle you're given, right? If you're given this angle, the x side will have a sine in it, right? The y will have a cosine in it, right? So it depends on the angle. That's the critical part. Focus on the angle, and from the perspective of the angle, what side is this? That's its opposite, right? From the perspective of this angle, what's its adjacent? What's adjacent to it? This side of the triangle, right? So always focus on the angle first. Don't just kind of assume that y and sine go together. They don't always go together. Okay, so this is just describing what's already given in the problem, right? We haven't really done the solution yet. Notice spending a lot of time in the setup. That's a good thing, right? Now we can think about some physics, right? So the physics of this is that this number should change, right? Why does this number change? Well, there is an acceleration in the y direction, right? So this number is not going to be 10 the whole time. Okay, that's noted. Now we come to the x component. This number does not change through the whole thing, right? Why? Because there is no acceleration in the x direction, right? That's 0 meters per second squared. If there's no acceleration in the x direction, the velocity in the x direction does not change. It cannot change, right? Okay, so that's a good thing to remember, right? So we can almost ignore the x part, right? Because we can kind of leave the x part alone because that doesn't do anything. It doesn't change. Only this is changing, right? The y component. So this is the before, right? So this is the before, right? At the beginning of all this. And then let's contrast that to the after, just before it falls to the ground, it strikes the ground. What does the velocity look like? Well, it would be pointing downward like this, just imagine the stone, kind of which way it would be traveling, right? So the velocity final, the vector, should look like that. And it also could be broken up into its component forms, right? So it's just x and y. There will be a vx, there will be a vy, right? This vx and this v naught x are the exact same, right? Because they don't change, right? There's no acceleration in the x direction, so that number is the same, okay? But this number is not, right? Vy, we'll have to figure out what that is, right? And we'll use a kinematic equation. Vy squared is equal to v naught y squared plus 2a y minus y naught, right? Why are we using this equation? Well, I'm trying to solve for the final velocity. I know where the stone starts and ends in terms of position, and I know the acceleration due to gravity, right? So I know all this information, and this is a good equation to use, right? Because this number is what we know. Initially, we have 10 meters per second, right, in the y direction. This number, a, is negative 9.8 meters per second squared. At the end, the stone is on the ground, which is 0 meters. Oh, I think I switched the coordinate system, which is fine. We'll do that. Use a different coordinate system. Okay, just to get some practice here, right? So initially, I can say the stone is 45 meters above the ground, right? You don't have to do that. You can stick to the old coordinate system. At the end, I can say the stone is at 0, right? So that does mean I'm using a different coordinate system. If you want to do this with the old coordinate system, it's totally fine. It's the same thing, right? So putting in the positions, right, and then putting in the acceleration, putting in the initial velocity in the y, you should be able to now solve for what is the velocity in the y direction at the end. Should be 31.3 meters per second. Okay, and that's not your answer, right? So don't throw that in just yet. Okay, because what we've done is figured out what's the vector of velocity at the end, and we can now put all the pieces together, right? So it's 17.3 meters per second in the I hat direction minus 31.3 meters per second in the j hat direction, right? This magnitude should be negative, right? Because this vector is made out of this vector added to this vector, right? The velocity's y component is negative, right? This velocity's x component is positive because it's pointing to the right, right? So the x component is positive, the y component is negative, right? So the vector velocity at the very end of all this is this. That's not what they asked for. They asked for the speed, right? So the speed is equal to the magnitude, right? So here's our vector velocity, and we put the bars to indicate the magnitude of velocity. Is you do the Pythagorean theorem on this, because this is in itself is a right triangle, right? This is a right triangle, right? So you can go a squared plus b squared, right? That sort of thing. So the square root of 17.3 meters per second squared plus negative 31.3 meters per second squared, take the square root of the whole thing, will give you 35.7 meters per second. And that is your answer, right? At the end, the speed of the stone is about 35 meters per second. Questions about that? ask questions, don't hesitate. We're moving at a pretty steady pace here because of the summer, so don't hesitate. Make sure you're slowing us down and making sure everything's sorted out, because I don't want to go too fast and miss something, right? So if something's clear, everything's clear, no problem. But if something's not clear, we'd rather you ask, right? Still good?
Yeah. Anybody has questions?
You can also, if something, feel free to read it out, or point me to it if there's questions. Oh, I forgot to start another thread for Instapol 2. Oh, cool, thanks.
A bunch of questions just if you wanted to.
For Instapol 2?
Yeah.
Cool. All right, let's.
They're asking to go the last step as well.
The last step in terms of this, I'm guessing, going from here to here.
Yeah, people are confused about the square root.
Okay, square root. Okay, it's cool. So hopefully you're okay with starting with this vector, thinking about its parts, right? X and Y. Think about a vector coming in parts, right? So the X part and Y part, potentially a Z part if there's 3 dimensions, but X and Y in this case. And one of those parts doesn't change, right? The X part doesn't change, so we can just copy over the X part, right? 17.3 meters per second. The Y part changes, right? This part is 10 meters per second positive, right? Pointing this way, and it becomes negative 31.3 meters per second, right? So that's this part of this vector. So once you have that information of the triangle, right? A vector and right triangles, kind of put those two together in your head, right? So here's the hypotenuse. The vector itself is always the hypotenuse of a right triangle. And now you have this side of the right triangle, and then you have this side of the right triangle, right? So then what you're supposed to do is find the hypotenuse, because right now we don't have the hypotenuse. We knew the hypotenuse of the vector, right? The magnitude of the vector at the beginning, it was 20 meters per second, because they told us. But once we're at the after point, right, where the stone is just about to hit the ground, we don't have that information, right? We don't have that number. We have to figure that out. And the way you figure that out is using your Pythagorean theorem, right? So because this, let me try to draw a smaller right triangle right next to it, is equivalent to this, right? A and B and C, right? So then A is your y component, B is your x component, right? So A squared plus B squared, square root is C, right? And so that's what I'm doing here. This is my x part and y part. Those act like the magnitudes of the two sides of the right triangle. So when I do that, I'm essentially doing A squared plus B squared, square root is C. Does that make sense? Is that what the question was, maybe? Right? If that doesn't, maybe that addressed it, maybe it didn't, but ask if that did. There's a question about, can we switch to the discussion? Yeah, there's a question about, can you use a different equation? Yes, depends on where you're using it, right? So you're using the initial velocity as 20 meters per second. Careful, because you shouldn't use that 20 meters in the equation, right? because 20 meters per second, yes, it's the initial velocity, but when you're applying kinematic equations now, right, because it's no longer one-dimensional, you want to split up into two parts, right? You want to do the initial velocity in the x and then the initial velocity in the y. So 20 meters per second, you shouldn't put it into any of the kinematic equations in this problem, right? If you switch back to the notes, you can put 10, right? That's an initial velocity in the y. And you can put 17, that's the initial velocity in the x, right? Those numbers can be your initial velocities for kinematic equations like this, right? But this number should not go into your kinematic equation directly, because that number is kind of the total, right, velocity of the stone. So it needs to be split up when you're using kinematic equations. So that's why the equation itself is fine. So if we go back to that discussion, this equation itself you can use. I'll give you a second there. But what I'm highlighting, that's a kinematic equation. It's fair game, right? But think of this equation now as v final in the x direction is equal to the v initial in the x direction plus the acceleration in the x direction times time, right? All these equations become now specific to your dimension, x, y, if there's a z, right? So all four of those equations, think of them as now doubled, if you will, right? Those four, now essentially you have 8 equations, right? If you want to think of it that way. Does the absolute value of the vector make it the speed? Yeah, so the absolute value of the vector velocity is speed, yes. Last equation. Oh yeah, how do you determine this as negative? Yeah, that's a good question. So switching back to the notes, I tend to do my trig in a way that just deals with the magnitudes of these sides first, because otherwise it's way too confusing, right? So when I do this sort of thing, I take the vector and I say, okay, this is the side of the vector. I am not necessarily paying attention to the signs right then and there, because I want to just focus on doing the sines and cosines properly, right? So in this case, I draw the velocity vector, I draw the right triangle, I figure out what the sides of the right triangle are supposed to be. Okay, that's 17, that's 31, right? Only after that do I think about, is this 17 positive or negative? Is this 31 positive or negative? Right? And the way I do that is I know this is the velocity vector at the end, right? Because if I throw the stone, this is the direction it'll be moving. And when I know that velocity vector's direction, then I'm thinking about how do I make it so that the x and y will add together to make this, right? Now, I pointed y this way, and I pointed x that way, right? And my claim is that if you add two vectors, right, using kind of our graphical way, right, if you add this vector to this vector, you start at the bottom of one of the vectors and go to the top of the other one, right? So the addition looks like this, or maybe use a different color, right? So the sum of this vector plus this vector is this vector, right? Now, if I didn't think this was negative, if I said, okay, actually, in fact, maybe I point the vector this way and I say x is that way, right? So when I add this vector to this vector, it's not this anymore, right? And then the graphical way of adding this is to shift one of them, right? You want to do tail to tip, essentially, right? So a vector you can pick up and move around as long as you don't change its length and as long as you don't change its direction, right? So if I pick this one up at the bottom and move it over here, right? And I say I'm going to delete this one, right? I'm just shifting this up. It's the same thing, right? That vector has not changed, right? Because I didn't change its length, I didn't change its direction. Now it's tail to tip, right? So I'm starting the beginning of one of the vectors and I'm connecting the dots all the way to the end of the other one. And so then this would be my result, right? So that is not how the velocity looks like for the stone at the end of the trajectory, right? As if you throw a stone, at the very end, it doesn't seem like it's going in this direction, right? It seems like it's going in this direction, right? So that's kind of how you reason why this has to be negative, because this is the part, right? This added to this makes this, right? And therefore, this has to be a negative number. So I do that at the end. I kind of reason the signs because it helps me kind of figure that out at the end. I don't want to do too many things at one place, right? I don't want to do the sines and cosines and also try to figure out what the negatives and positives are, right? You want to break up problems in a way that makes it easier for you to catch mistakes, right? And make sure you're doing the problem correctly. So I try to break it up into small little parts just to avoid making any errors along the way. So at the very beginning of the class, I said, okay, this whole class really has two big ideas, right? The idea of momentum, the idea of energy, right? And those are the big ideas that we want to get across. So far, we haven't talked about either of them. We're still building our vocabulary to get to these big ideas, right? So we're talking about displacement and velocity, acceleration. We're slowly building the vocabulary to get to these big ideas, right? So today we're going to start with the momentum idea, right? The momentum principle. And when we're thinking about this, right, we're moving towards thinking about what causes motion. And the fancy term for this is dynamics, right? So kinematics is describing motion. Dynamics is about what causes motion, right? And we're essentially going to start talking about forces, right? So a lot of you are in the life sciences. Here's a diagram of the human body. Think about the muscles in your body and how they can apply forces, right? This is important. You can't walk, you can't move around, right? Swim, right? Eat. All these things are done, right? Because of forces being applied, right? Something's pulling, something's pushing in your body to make this happen, right? So, going to our notes here, we're now talking about Newton's laws of motion. Okay, and essentially the big idea here revolves around momentum, right? So that's the big idea of the class that we're going to try to get to, right? Now, before we write down Newton's laws of motion, let's pause to think about how you would maybe think about going about writing the laws yourself, right? Imagine you are living in a time before Newton, well before Newton, and you want to come up with certain ideas of how things work, right? Why things move. So from everyday experience, right? So if you have an object, here's my water bottle, and you're pushing it, right? You might have figured out there is such a thing as a push, right? I put my hand and push. That concept, right, even though we call it force, that concept would have existed. People would have realized you have to push, right, in certain situations to get things to move. So let's use our modern word for it. We'll say force. We know it's a vector because it matters which direction you push, right? So you know from experience, if you're trying to move a box, if you push one way versus the other way, right? If you're trying to lift the box or glide it across the floor, you have to push in different directions, right? It could be the same amount you're pushing by, but the direction matters, right? And the other thing you might notice is that, okay, this force you're applying has something to do with how big something is. If you're trying to push an elephant, right, you're not going to really succeed very much, right? Versus a pen, right? So if you're just trying to move a pen. So you have an idea that this force you're applying has something to do with the object itself, right? So certain objects are much more difficult to move. Certain objects are much easier to move. This idea you would have known before Newton, right? And before Newton, you probably saw that if you push something, it moves. But if you stop pushing it, it stops moving, right? So if you see something in motion, right? So my pen, you would assume, okay, something's pushing it, otherwise it wouldn't move, right? Because that's your everyday experience. Because if something's just sitting there, it just sits there. It doesn't move by itself, right? So you might say, okay, there's something to the mass, and it's something to do with how it moves, right? Using modern terms for this, maybe back in the day they called it something else, that doesn't matter, but you might have said this is kind of how reality works, right? If you push something, it moves. It's harder to move certain things, but easier to move other things, right? So if you look at this, it kind of looks like maybe what you're expecting to see, right? You're expecting to see F equals ma, but I just want to kind of reason our way there, right? To think about what would your experience be in everyday life. That's important, right? To kind of factor that in. This is what your everyday experience would tell you, and it's okay, not bad, but it's not accurate, right? It's not how the nature works, right? But it's a good attempt. We try to kind of reason our way to this idea, right? But let's think about what Newton did. Newton wrote down the second law, more on why we start with the second one in a bit. The second law, Newton comes along and says that yes, there is such a thing as a force. There could be multiple forces on an object, so we want to account for that. So we call it a net force, the net result of all the forces, right? We can figure out how they add together. That is equal to, right, that causes a change in this thing called momentum over time, okay? So Newton's second law, essentially in its original form, is this. Right? Again, not F equals ma, right? That's perhaps what you're looking for. But this is the original form of Newton's second law, is that a net force causes this thing called momentum to change with time. It's a derivative, right, from calculus. It's a change with time, okay? So there's a lot in this equation, even though it seems small, right? There's a lot of information that's actually packed into this. If you were to write in words everything that this equation says, it will take you a paragraph. It'll maybe take you several paragraphs to properly describe what this equation is saying, right? That's the advantage of math, is that you don't have to spend 3 paragraphs writing this down, right? In 1,000 words or something, right? You can write everything in a very compact way, but it's a little bit deceptive because it does hide a lot of information, right? Okay, so we'll take it in parts to understand what all of this means, right? So the first thing we want to try to understand is, what does F net mean? Okay, what does that mean? Okay, when we say force net, F net, what we mean is that we want to sum, Greek symbol sigma, all the forces that are external to an object. Okay? It doesn't have to be just one, right? So in the case of me pushing my pen, there's one force that I might obviously see, right? In the sense of I'm pushing the pen, I might see one force. It doesn't have to be one force. It could be 100 forces acting on the pen. And what we're doing is saying we're going to add them all up, right? And remember, the force is a vector, so when we say adding vectors, right, it's not just adding a bunch of numbers together, right? It means adding the vectors together. So let's say we take an example, right? We'll take an example of a table here, and then on the table is a book. Okay, and let's say you are pushing on the book from this side, call that F1, and that's you. And then on the other side is your friend, also pushing on this book, F2 is your friend, right? Now, let's think about the forces acting on the book, okay? And remember, Newton's second law only cares about the external forces, okay? We'll get into what that is. So external forces, okay, what are they external to the book? Well, your force, the force you're applying on the book, your friend's force, right? Gravity's there. More on that later in the class, right? So gravity is acting on the book. right? What else? Well, there's a force from the table on the book, right? The table itself is pushing up on the book, right? So that's another force. So we're identifying all the forces, right? All of the forces are important to consider. Okay, that's external, but what we're not considering, right? Not considering the force that the book applies on the table. Okay, there is that force. The book is pushing on the table, right? If you don't believe it, put your hand under the book, right? You can feel that the book is actually pushing, right? So that force is not considered in F equals the change in momentum over time, right? When we talk about F here, the net force, we mean all of these and not this, right? Not what the book does, not the object's force, right? So when we're doing this, we're focused on the book and we're thinking about, okay, what's affecting the book, right? What's external to the book, and that's really important, right? Okay, how are we doing so far? Anything, quick questions popping up? Okay, cool. Keep asking questions, right? So I'm just kind of taking our time, trying to digest every little thing about this equation. Very, very critical idea, right? This is the momentum principle, right? This is very, very critical. So we want to take our time making sure we understand what this is, right? Okay, so we talked about the left-hand side, the net force. What does that mean? Let's talk about P here. I said that was momentum. Okay, so what does P mean? Also a vector. It also has a sense of direction, right? And momentum is defined as mass times the velocity, right? So notice that thing we kind of had some intuition of creeps back in, right? It's not related to the force, mass times velocity, right? Our intuitive kind of understanding that big things and how fast they move somehow are connected together. It's not directly to the force, but close, right? There's a time kind of factor to it, but that factor shows up again, right? So there is a property, right, that nature seems to care about, right, called momentum. It does kind of keep score, right? This quantity matters. So why is it useful? Because keeping track of this is really important, and we can kind of see, did the momentum change, right? If the momentum changed, we can say something about what happened to the object, right? If the momentum didn't change, we can say something very definitive about the object, right? So this is an important idea, this idea of momentum, right? It's a little abstract, right? Because it's not as clear as velocity. It's how something moves per time, right? You can kind of think about it in terms of a speed with a direction. It's a little more abstract because it's mixing two ideas of how much stuff something has, its mass, more on that later, right? So mass is quantity of how much stuff does the something have, right? The more stuff it has, like an elephant has more stuff, right? More mass, then for the same velocity, it would have more momentum, right? So it's a quantity that keeps track of two different ideas. Momentum is about mass and velocity combined, right? Okay, so far, what we have not talked about is kind of the obvious second law, right, that you may have seen in the reading, or if you have experience with this before. The obvious one you're looking for is F equals ma, right? And you might say, where the heck is so far not a citing of F equals ma, right? Or what happened? So let's see what happened to F equals ma, right? Okay, bit of a mystery where F equals ma went, right? It's here. It's kind of hiding in there. if you take Newton's second law, right, the net force causes momentum to change with time, we can rewrite it as this, right? The derivative, and then instead of P, we'll just put in the definition of what momentum is, mass times velocity, right? With a simplifying assumption, if, big F, mass is constant, right? That's many cases, right? Your mass is relatively constant, right? As you walk across campus, your mass is not significantly changing, right? If you are pushing a box across your room, the mass of the box is not changing by a whole lot, right? So very basically constant. So you are going to see a lot of situations where the mass is constant, right? So it's not simplifying assumption that is too bad, right? There's a lot of examples where mass is actually constant. If that's the case, what you can do with the m there is to pull it out of the derivative because it doesn't change with time, right? So we'll pull the m out, and that means what you're left with is the derivative of velocity with respect to time, right? Notice that the derivative, instead of applying to mv, will just apply to v because the only thing that's actually changing is v, right? And we know what this is, right? The derivative of velocity with respect to time is equal to acceleration, right? So this is where F equals ma comes in, right? So the net force causes an object to accelerate, right? So that's coming from the original form of the second law, right? 4 cases where mass is constant, right? So when you're doing F equals ma, you have already assumed that the mass is constant. F equals ma does not work for a rocket, right? A rocket in particular loses a significant amount of its mass, right? The starting point of a rocket before it launches, something, let's say 80-90% of the mass is fuel, right? So that's a significant change of mass. So you're not applying F equals ma to a rocket. You can, in fact, go back to the original and apply this, right? So this works for a rocket, right? This is the better, more general form, right? So when you're looking at specific instances, okay, fine. You have to be careful about when they are valid and things like that, right? All right, I should pause here. So are there questions before we go on?
Someone asked why, when considering net force, it's change in momentum instead of just the momentum itself.
Right, yeah, so that's a good question. I think it's something to ponder about. And the short, I think maybe the answer is that it doesn't quite work out, right? So if you think about, okay, there's no time component, it doesn't seem to work that way, right? Maybe you're saying, okay, I apply a force and then the momentum changes because of the force. That doesn't fit the reality, right? There is a time component that seems to fit together to make all of this work, right? There has to be some time factor. It's a force applied over some time period that seems to change momentum. A force itself doesn't change momentum, right? It changes momentum over a time period. So time is an important factor. So there's probably a deeper philosophical reason why time has to be involved in all of this. But the short answer would be, think about what works, right? So we can do experiments to demonstrate that this does not work, right? And I'll talk about that in a second. Yeah, so when we talk about the first law, maybe a little bit later today, if not next time, you'll see that there's another reason why this is not correct, because it turns out that you don't require force to have something to move, right? So it's through experimentation and kind of trying to fit the model to the reality, kind of making sure that the model and reality are going together. Do you come up with the principle, right? Because it's one thing to say a principle, but if it doesn't apply to experiments, then it doesn't work, right? So then you come up with the idea and say, does this work experimentally? And there has to be confirmation in both directions, right? The model and reality. If you push a book, what does it do, right? So yeah, that's a good question. Other questions? Nope. Okay, cool. So why don't we try out an Instapol, skip number 3, and then go to number 4. And that way you're thinking about forces acting on an object. Again, when you read a question, make sure first thing you're doing, jotting down on your notes a sketch, right? A simple diagram of what's going on. So let's do that. Let's take a minute, have you do work on it, get started, and we'll check up on you in a minute. Okay, switching over, yeah, thanks for starting that, Jericho. Okay, keep working on it. I'm going to switch to the DocCam here so that I can start sketching out a diagram. Okay, two kind of sets of directions to keep track of here, right? So they're using north, south, east, west, right? That's kind of in everyday speak. If you were talking about moving or traveling, you're talking about north, south, east, west, right? But you wanted to sometimes translate those directions into the x and y coordinate system, right? So that's kind of how we do math using x and y. So there's sometimes translation you need to do, right? So oftentimes better to think of it bird's eye view, looking down on what's going on. There is a box, right? And there are two forces applied on this box, right? So the box itself, we're told, has a mass of 50 kilograms. And what are the forces? One force, 60 newtons, is acting towards the south, right? So south is downward, so we can say this is the direction of the force, 60 newtons. And there's another force, 80 newtons, they say is acting to the east, right? Which is our positive x direction. Okay. And they want to know what is the magnitude of acceleration of the box, right? So now notice that it's no longer 9.8 meters per second squared, right? The acceleration that we said was a number for free fall, now it's open, right? Because that number is dictated by the net force. Right? So if there's a net force on, say, a box or you, right? How you accelerate, now that's open, right? So it depends on the force, depends on the mass involved, right? Okay, So let's think about kind of a couple ways of doing this problem. I'll just do it in 2 ways for practice. One is to think about, okay, this is our big idea now to apply, right? It's no longer kinematics. It's not just describing motion. We have to talk about forces and why things move. This is our big idea. It's really this, but oftentimes in practice, because mass is constant, we will just use this. F equals ma, right? So we can get the acceleration so long as we know the net force, okay? So we have 2 forces, right? And we have to add them together. They're vectors, so you do vector addition, right? So from looking at them here, you can say, okay, so when you add these together, the net result should be a force kind of like in that direction. We'll call that force result, right? So vector 2 is pointing that way, right? When you add this vector to this vector, you will get a vector that kind of points in that direction, right? Notice that this, you can make it into a right triangle, right? Always, when you think about vectors, think about right triangles, right? Hypotenuse is the vector itself, and then try to make a right triangle, because if you're trying to find the hypotenuse of a right triangle, try to figure out, okay, what are the sides, the other 2 sides of it, right? So in this case, we know this side of this right triangle, we know what this side of the right triangle is, right? So if we're looking for the magnitude of this force, the resultant force, we are going to do the Pythagorean theorem, take the square root of 60 newtons squared plus 80 newtons squared, right? Take the square root, and then you get 100 newtons. That's your resultant force, right? The magnitude of the resultant force. It points actually in that direction, right? Now, we need to find the acceleration. That's what they said, right? So our big idea is that the net force is equal to mass times acceleration. Whatever the direction of the net force is the direction of the acceleration, okay? Whatever the direction of the acceleration is, it's the direction of the net force, right? This is a vector, and all that the mass is doing, it's a scalar, right? It's some number and units. All that the scalar is doing is just multiplying the vector, and a scalar that multiplies a vector, it either makes this vector longer or shorter, depending on this number. It cannot change the direction of the vector, right? A scalar cannot change the direction of the vector. So we have a scalar that's multiplied by the vector, and so what this is saying is the acceleration and the force are in the same direction, right? Okay, so in that case, we can kind of ignore the direction because the direction is that way, right? The acceleration will be in the same direction as the force. So we can, because they are asking for the magnitude, we can say, okay, if we say the force, net force is equal to mass times acceleration, dropping the arrows, because I'm just using this as magnitudes now, I can say the acceleration is equal to the net force divided by the mass, right? So that's 100 newtons divided by 50 kilograms will give us 2 meters per second squared. Is that okay? Kind of makes sense? Okay, that's probably the easiest way to do this problem. Is to just find the net force, divide by the mass, and you're done, right? You get the acceleration, it's 2 meters per second squared. But just for practice, what we want to do is think about this equation. And I said before, if you actually was trying to write down Newton's second law in words, you will actually have to write several paragraphs because it has a lot of information. And one of the pieces of information that we haven't talked about yet is that this isn't a single equation, okay? So it's multiple equations. When we say F equals ma, this really is 3 equations. 1, 2, 3. Okay? That's why the math way of writing F equals ma is somewhat deceptive because there's so much hiding behind the scenes, right? And that's just because mathematically there's a way to pack a lot of information in math, right? In a very short kind of notation. That's an advantage because you don't have to keep writing 3 equations every single time. But it's also somewhat of a disadvantage sometimes, especially in the beginning, because it's not obvious that this is actually 3 equations. Okay? When we say F equals ma, what we're really saying is you need to sum up all the forces in the x direction, and that's equal to the mass times the acceleration in the x direction. You have to sum up all the forces in the y direction, and that's equal to the mass times the acceleration in the y direction. And you have to do that with the z direction, if there is a z direction. Okay? So this is really 3 equations. In practice, when you're using F equals ma, oftentimes you're actually having to break them up into x and y components. So your kinematics, right, 2-dimensional projectile motion kinematics is helpful there, right, because you're already used to this idea of x and y having to be treated separately, right? You have to deal with them individually, x and y separately, and you want to get in that habit and that mindset, x and y, they're different things, right? Separate them out, right? So to practice this, let's do the Instapol in kind of the longer way, just so that we practice that, right? Same problem. What I'm going to do is say, let's sum up all the forces in the x direction and say mass times acceleration in the x direction, right? And we come back here, what are the forces in the x direction? Just the 80 newtons, right? So what that means is the 80 newtons is equal to 50 kilograms acceleration in the x direction, okay? And that means we can solve for the acceleration in the x direction is 1.6 meters per second squared. All right? Not our answer. They wanted the acceleration of the box. That's not it, right? That's part of it. Then we sum up all the forces in the y direction and say mass times acceleration in the y, right? And same deal, we come and say, okay, what are the forces in the y direction? There's only one, 60 newtons pointing downward, and that's negative, right? So negative 60 newtons is equal to, the mass is the mass, right? So 50 kilograms, acceleration in the y. And then you solve for the acceleration y is minus 1.2 meters per second squared. Again, not the answer, but just part of the answer, right? So now what you have is the vector acceleration and its components, right? And that vector acceleration looks like that, right? That's your acceleration. Again, you can form a right triangle, right? When you're doing the components x and y, what you're doing is finding the components of the sides of a right triangle, right? So here's a right triangle. And you can find the magnitude of acceleration using the Pythagorean theorem. You say 1.6 meters per second squared, square the whole thing, and then minus 1.2 meters per second squared, take the square root of that, and you'll get 2 meters per second squared, just like before. Same answer, just a different way to do it, right? So in this particular Instapol, this is the easiest way to do this. I wouldn't recommend kind of going through all of this. However, when you take a quote-unquote easy problem and apply the kind of the more sophisticated approach, it kind of gets you thinking about doing this, because in the future, when we do a problem, we're going to do this, right? You have to do this because this is the detail that we're going to get to. So just so that you have a reference point, I'm having this here so that you are aware that when we say F equals ma, it's actually 3 equations, right? It's not just a equation. So when maybe if you saw this in high school, they would have just written out F equals ma, right? That's fine. It's a good start, right? It's a simple form of it. But what we want to do here is try to understand the more sophisticated, complete kind of version of things, and that version involves the fact that this equation is actually really 3 equations hiding in there, right? All right, quick questions before we go, or do we address most of it? we got everything? Okay, cool. So we'll stop here. We'll pick it up tomorrow. Make sure you're starting on your homework if you haven't done that already, right? So there's going to be 2 due on Friday. The first homework was supposed to be due today, but since, we're still getting started on the class, I figured I'll delay it till Friday. But there are 2 homeworks. Those 2 homeworks are going to be what you're going to be expected to know for midterm 1, which is in 1 week, right? So we'll get you ready there. So come talk to us during drop-in hours, and we'll see you tomorrow.